Robomi here, 33-year expert in sulfur recovery with Sulphur Experts. As you know, many of these videos are based on questions we receive from our clients, and in the past few months a number of you have come to us with problems with your tail gas unit or TGU burner. As you may know, that TGU burner is at the very front of the tail gas unit, the first thing the gas comes to from the sulfur recovery unit. It does have a number of different names depending on who you bought the technology from. TGU burner, TGU heater, very commonly the RGG or reducing gas generator. No matter what term you use, it's that thing at the beginning of the tail gas unit. We're going to describe what it does and how to operate it properly. I won't be getting into exact design details, but just to show you a few pictures, these TGU burners can be what's called a can inside of a can style, where the flame from the burner is inside a chamber, the process gas from the SRU comes around it, or it can be something where the burner has its own little section time before the tail gas from the SRU comes in and mixes with it. We won't get into those sort of details, what's better or worse, but yours may be either one of those two designs. What we want to talk about are the purposes of the TGU. There's two things we're trying to do in this burner. The first one is to get the gas up to the right temperature for the TGU reactor. Depending on the type of catalyst you have there, regular or low temperature versions, that could be anywhere between 220 Celsius and 280, perhaps 460 Fahrenheit up to 540 or higher, somewhere in that temperature range. The second thing we're trying to do with this TGU burner is to guarantee we have enough hydrogen and CO, commonly called reducing gases, for the tail gas reactor to do its job. Because that TGU burner can make reducing gases, it is commonly called a reducing gas generator or an RGG, which may be the name at your facility. So heat up the gas, make some hydrogen and CO. What I want to start with is the myth that the reducing gas generator, the TGU burner, makes all of the hydrogen and CO. The SRU itself makes lots of hydrogen, lots of CO, and this graph shows 20 plus tests that we've done at plants. The blue at the bottom is how much hydrogen and CO was already there from the SRU or the Klaus tail gas versus how much was added by the TGU burner. As you can see, the TGU burner really doesn't make a lot of hydrogen and CO. You could live without the production. You could live without any hydrogen, any CO being generated there or added at that location. So just to kill that myth, we won't get into it further. You can contact us if you don't believe me or want to examine it. That second purpose that I mentioned for the TGU burner to make hydrogen and CO really isn't there. If we make a little bit, great, but we already have enough in the Klaus tail gas. So the real purpose of this burner is not to make hydrogen and CO, but to avoid the bad things. I want to run this burner so that I don't have oxygen coming out of it, which will sulfate and deactivate the catalyst. And I don't want to run it where I make soot, which will plug the catalyst. A bit of a complicated diagram here for you. If I run that burner at excess stoichiometry, I will have oxygen come out. Above 100% stoichiometry, above perhaps 9.5 to 1 when it's run on natural gas, I'll have oxygen come out of that burner and deactivate the catalyst. If I go too low in stoichiometry, I'll get rid of the oxygen, but then at that point I run the risk of making soot and plugging things. So the perfect stoichiometry is around 95%. Many of you will run 9.5 to 1, somewhere in that range on natural gas to get that perfect stoichiometry. So we don't really need to make the hydrogen and CO. What we really want to do is avoid killing the catalyst. We want to run that at the right ratio to do it. We set it up at whatever ratio gives us around a 95% burn in that tail gas burner. The biggest problem with these things, and one of the key rules for any engineer, is never trust your metering. You set it up at 9.5 to 1, 9 to 1, whatever that perfect stoichiometry range is, no oxygen, no soot, but either the natural gas or the air meter's off by 10%, and now you're accidentally into one of those bad ranges. So we're going to walk through how we confirm the stoichiometry, making sure that burner is working properly. Of course, we want to check the metering, make sure it's accurate. We want a fuel source like natural gas that isn't moving around in composition all the time. But even that's not good enough. Even the best metering can be bad enough that we're going to have some problems. So we set it up at the right, what we believe is the right stoichiometry. One way to confirm it, and people love this, it takes you back to high school, to university, is to look at the color of the flame in this burner. If you remember playing with a Bunsen burner way back when, excess stoichiometry, a blue colored flame. Sub-stoichiometric, a yellow colored flame. Right at that transition, some people call it a pink color, but you transfer between those two color ranges. That would be perfect, except I bet 95% of you have no ability to look at the flame. You might be able to look into the burner chamber, but then all you see is glowing orange refractory. You can't see the flame separate from that. So if you're lucky enough to be able to see the flame color, that color chart is one way you confirm the stoichiometry. Where it changes from blue to orange, that's the stoichiometry limit, that's 100%. Just dial it back a few percent from there. Really, however, we would like better ways than that. We would like to actually measure what that burner is doing. And we can do a couple of simple measurements. One way with a proper oxygen analyzer is to measure what's coming out of the burner. We shouldn't see any real measurable oxygen. Definitely we don't want to see more than 100, a couple of hundred parts per million. If you have a type of oxygen analyzer that can measure low levels, if you properly protect it with a filter so it doesn't plug, you can grab samples from the outlet of that burner. If you see more than a few hundred ppm oxygen, you can dial the ratio back until it disappears. In the other direction, we know we don't have oxygen. What about soot? You may or may not know it, but you can do soot measurements. They're not very fancy. Simply hold up a piece of white tissue, perhaps a tube full of a white filter material. If the burner is making soot, you will see it in the process gas. Open up the sample point, measure or flow the process gas through one of these devices, and see whether there's soot there. If there's no oxygen, if there's no soot, if you're doing those measurements properly, you know you're in that correct range. So you can use those simple ones to dial and make sure you are where you want to be. Slightly more complicated, most of you can't do this yourselves, we do this when we come to site, is to use that same graph I showed you earlier, and as oxygen disappears, as you go sub-stoichiometric, hydrogen and CO, the blue and the purple lines, start to increase. So if you can measure in and out of that TGU burner, the process gas going in and out, and measure the change in hydrogen and CO, you know exactly where you're at for stoichiometry. So that's kind of a mixture, simple tests like oxygen and soot, more complicated tests like CO and hydrogen. Those will help you dial that burner in perfectly, and it won't do any damage to the downstream catalyst bed. The very last choice you have is to throw the burner away completely. It's one of the reasons that the catalyst vendors, the TGU catalyst vendors, have invented low temperature catalyst. So we can throw the burner away, we can put an indirect steam heater in there with 600 pound, 40 bar, 4000 kPa steam. We can get to the temperatures that these new low temperature catalysts work at. We no longer worry about soot. We no longer worry about oxygen. We don't worry about burner management or keeping this thing lit and online. All of those problems go away. So hopefully that helps you a little bit. The TGU burner is the Achilles heel of the tail gas unit. If you don't get that ratio, that stoichiometry perfect, you can kill the catalyst, deactivate it, or plug it. You always want to confirm the metering using some of the checks that we just discussed here today and get years, if not decades, out of your tail gas unit catalyst. I hope that was informative. If it was, please feel free to sign up for our channel. Don't forget to ring that bell, send us some questions if you have them, and we'll see you in the next video.